I'm Mike Dascal, VP of Quantum Technology at FCAT. And seeing as 2025 is the International Year of Quantum Science and Technology, we thought it'd be worth going through some of the milestones. Towards the end of the 19th century, many thought that physics was done, that there were no more fundamental laws to uncover, just details that needed to be ironed out. But in 1900, Max Planck was working on one of those so-called details, a problem that appeared in the theory of how physical systems radiate energy. And to solve the problem, he introduced a novel idea, that energy isn't continuous, but comes in tiny packets, or quanta. It was a radical idea, but it would be quickly validated with Einstein's work on the photoelectric effect in 1905. The first quarter of the century saw physicists trying to make sense of Planck's postulation and what followed. But the theory wasn't formalized until 1925, when Heisenberg, Born, and Jordan developed matrix mechanics, a new way to describe physical quantities that really defied intuition. 1 year later, in 1926, Schrödinger offered a second formulation, one that described quantum states as waves. This would open the door to the quantum world even further, and the Schrödinger equation, describing how quantum systems evolve in time, would become a cornerstone of quantum physics. Just 2 years after quantum mechanics was first formalized, Heisenberg would discover his famous uncertainty principle, proving that for certain pairs of physical quantities, knowing more about one means knowing less about the other, and that neither can be known with perfect accuracy. It was likely this result that eventually led Einstein and Bohr into a heated debate at the Solvay conference just 7 months later, now one of the most famous physics conferences of all time. This is where Einstein famously said, "God doesn't play dice," to which Bohr apocryphally replied, "Stop telling God what to do." Einstein's view would become a little clearer with the publication of his paper with Podolsky and Rosen in 1935. Here they argue that quantum entanglement, later described by Einstein as spooky action at a distance, seems to imply the impossible, and so something in the theory must be missing, must be incomplete. There must be some hidden variables somewhere to explain it. Schrödinger's cat was written as a small note in a paper that challenged the limits of quantum theory. He also thought there must be something wrong or missing from the theory, and he demonstrated the problem by showing that it predicts a cat can be both alive and dead at the same time, despite what our experience tells us. In 1964, John Bell made a remarkable discovery. It was possible to prove that there are no hidden variables in quantum mechanics. In other words, it's possible to prove that the theory is complete and that the quantum world is very different from the one that we experience. The first so-called Bell tests that would prove out Bell's theorem would be conducted in 1972, and stronger results would be recorded up until 2016, where multiple experiments, almost simultaneously, finally closed all the loopholes to prove quantum mechanics is complete and Einstein was wrong. Perhaps the most famous moment associated with early quantum computing came from Richard Feynman. At the first conference on the physics of computation in 1981, he's quoted as saying, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." In the years that followed, many began thinking about how quantum resources could offer new computing capabilities, with the first quantum algorithms and quantum communication protocols appearing in the early and mid-80s. But in 1994, Peter Shor made a milestone discovery, a quantum algorithm that could crack classical encryption. Suddenly, quantum computing wasn't just theoretical, it had real-world consequences. The first quantum bits, or qubits, appeared in the late 90s, with very limited quantum computers appearing in 1998 and 1999. Maybe a bit generous to call them computers, though. Since then, quantum computing has evolved tremendously. We now have many ways of building qubits, and the scale of these devices has grown from a couple to dozens, to hundreds, and now even into the thousands. We still have a long way to go before we have fully functional and useful systems. Our computers are still very small, and because of the nature of quantum systems, they're very error-prone and difficult to control. Progress is advancing though, and small fault-tolerant computers are expected to appear in the next 5 to 6 years. As we approach full-scale, error-correcting quantum computers, work is continuing to identify precisely where these systems will be advantageous. We don't plan on using them to break encryption after all. We're also preparing for the post-quantum cybersecurity era, as it's crucial to start upgrading encryption systems and building new quantum-resistant technology to keep us safe in the coming years.